Hello everybody, and welcome to this XP Live webinar. My name is Nicole Highhouse, and I'm the Marketing Manager here at XP Solutions in our Portland, Oregon office. Today's topic will review methods and techniques for 2D model interrogation. If that's what you're here for, you're in the right place. For those of you who may not be familiar with XP Solutions, we have a long history of providing high-performing software solutions. Our intention is to make sure that in your work, you can model with confidence. Now, this means that we strive to provide excellent customer service and support, and that we offer continuing education opportunities for engineers in our industry. Which brings us really to today's presentation. Today's presenter is John Howell. John, who works out of Huntsville, Alabama, has about 25 years' experience in the modeling and simulation world. Prior to joining the XP team, he worked with both Wallingford and Bentley software companies. Before that, he was involved with commercial software for computational fluid dynamics, so he is one of our XP experts. Thank you for joining us, and John, would you like to take it from here?
Okay, so thank you, Nicole. So today we're going to look at some creative ways that we can interrogate 2D models. And so in today's agenda, I'm basically going to break that down into three sections. There's going to be the model setup section, because a lot of the outputs that we get with 2D models, we have to set that up in the model build process. We're going to review some of the model summary data, because there's a lot of useful information within the model summary data, as part of the solution, reviewing model solutions, but also in the sensitivity analysis process that happens as we create complex models. And then we're going to be looking at post-processing and analyzing fully completed models. So basically break it down into three sections today. So the first section is model setup. There are a lot of different types of data available in a 1D, 2D model. There's various element data in the 1D model, the node and link data, information about when a node surcharges or the flow rate in a link. There's various data from the 2D model elements, such as depth or velocity at a cell. There's a lot of summary data available in both those models, the 1D and 2D models, such as total flood volume at a node, the mass balance of the 1D solution, in the 2D model, peak depth at a cell, or peak velocity at a cell, or time to peak. So there's a lot of good tabular information available in the summary data for both models. One of the things that we need to do in using XP Swim is actually tell it the different types of output we want from the 2D model. We have the usual suspects up at the top of this dialog box here: flow, velocity, depth, and water elevation. There's a lot of other creative ways we can use the data within the 2D solution engine. You see all these hazard result types. Those are kind of particular to the UK, but we'll show hazard today in our model as defined as velocity times depth. So we'll have to turn these on to make them options as part of our 2D results. There's other things we do at model setup, such as setup parameters like time to inundation. We have to specify the range that we want to display as output. There's other things that we can do during the model setup process where we're actually using reporting on 2D data and using that 2D data, such as a section profile. In the model that we see today, we'll have a 1D channel. When I'm creating that 1D channel model, I may not have cross-section data. Having 2D data, such as terrain data, allows us to actually create a cross-section based on the terrain map using the section profile tool. We can then immediately export that cross-section information and import it into the 1D channel model as a natural channel shape. So there's a lot of ways we can interrogate the 2D surface to help us build the model as part of the model construction process. Other things we might do in a pre-processing or model setup function, sometimes we set up a model with a very sparse grid just to kind of as a sanity check to make sure that the model's proceeding properly. We might see an early area of overflow during an initial run. We might want to put in time series outputs, such as flow boundaries. These are really cool tools. In XP Swim, they're very useful. The flow time series output flow boundary is basically a polyline that I can drape anywhere on the terrain map, and it's going from left to right downstream, and it's going to report the amount of flow that crosses that boundary. So I like to think of it as a microphone or an interrogation point at any point in the model. Another option we have is to put in head and velocity outputs in the model. And again, I think of these as microphones. They're just points that we can see throughout the model, and these points can be reported on at any time step in the model. And in this case, it'll give us velocity and velocity direction of flow anywhere on the 2D surface. So those are nice tools that we have in XP Swim that you will see throughout the model during the model construction process. So once we're through with the construction process and we've run the model, there's a lot of good information that comes from the model as summary data. In the 1D output logs, there is element level information in the sections that you see here, and this is information that's available for these elements at each time step. So if we want to dial into one part of the 1D model and see what's happening at any time step, the 1D output logs, the tabular format is a great way to go look at that. There's a lot of summary data in the 1D output log as well, particularly the mass balance and in the numerical model judgment section. We're dealing with two separate numerical engines, a 1D engine and a 2D engine, so we have two separate output logs. The 2D output log gives us a runtime summary at the start of the output log, and then at the end there's some very useful information about peak flow in, volume at start, volume at end of the run, total volume, cumulative mass error, etc. for the 2D domain. And finally, we have a lot of good 2D summary data that's available within the model. This will be a good time to, before we get into the results analysis, exit the PowerPoint presentation and bring up XP Swim. And if we actually go to the 2D summary, like in the screenshot that we saw before, there's a lot of good summary information here. I can look at the change in volume over the course of the solution. I can look at cumulative mass error over the course of the solution. We always want to keep that less than 2, so we achieve that in this model. The flow in values and the flow out values as part of the 2D summary. Now this is summary data. I can actually take this data and export it if I wanted to using the customization or export dialog. Also, the information in the header is useful. You might want to copy and paste that if you're preparing a report. Some of that information can come in handy. But beyond this, in the 2D job control, if I actually want detailed 2D information, summary information, I can go into the 2D job controls, and I can actually specify that check files be produced. And these check files can report on, well, the check files give me a ton of information about what's happening at each time step in the 2D model. So I can actually export to CSV file in 2D information at each time step, and that can be useful summary information as well. So let's start transitioning to what we can interrogate in the model once we've had a model run. One of the first things that we can look at in a model is where we might have potential problem areas. I'm going to turn on the links so that you can see those. And one of the things that we can do in the 1D realm that has an impact in how we interrogate the 2D model is what's happening to these 1D elements. One of the things we offer in XP Swim is graphical encoding. I like it because it's very quick and easy to use. In this case, I've graphically encoded my nodes based on the time flooded, and I've graphically encoded the size based on the volume at that node. And as you can see, just from this simple interrogation, we obviously have some issues up the center of the model here, where we've got surcharge and flooding at the nodes, and we see the green area over here, which probably will require less interrogation as we go through the simulation, because we don't see very many problems over there. But graphical encoding is a very quick, down and dirty way to immediately begin getting some feedback from the 1D elements that can impact the 2D portion of the model. One of the great things about 2D modeling is it allows us so many ways to look at data that's generated from the model. So down here are some of the scalar values that are available to me as 2D results. One of the first things we want to see is where is it flooding? If we're running a 2D urban flood model, where do I have water exiting the 1D elements and escaping to the surface of the model? So we have these nice scalar displays. I clicked on water depth, and I get this nice thematically mapped filled contour display. Okay, there's a lot of different ways we can look at the information in XP Swim. I like this because it's nice and pretty and it has lots of colors in it. That's all great. But we also have control over how we want to display this. I've got a color ramp here that I like because it indicates to me where there's the water depth kind of implies risk, and although we specifically mapped risk as a scalar value, and we'll show that later, I like this display simply because where the water is the deepest and where I may have the greatest problem area in terms of depth, I've colored that orange or red, and I transition to these more friendly colors at the edges of the solution. But you have complete control over the color ramp. You can see that you have these pegs that you can slide up and down, and you can thematically color this however you want. There are a lot of different ways, though, that we can look at the model. We don't have to look at it as filled contours. We can just look at it as contours, right? So let's click OK and look at contours. Now this gets busy real quick, and why is that? Well, if we go back and look at the properties for contours, we can see that I have contour labels turned on, show contour labels. And so what it's going to show me is the depth at each one of these contours. And right now, because I've selected contour lines, and there's a lot of change, it gets real muddy. This is useful, though, as I zoom in. I now have depth values associated with each one of the contours here. And this may be useful information if I'm preparing a report and want to zoom in on some section of the model and report these values out. And to do that, and by the way, as a side note, at any time in the model, I can always click under the Tools bar and export these graphics. So any of the thematic elements that you see me using today, or the visual tools that I'm using, once I've rendered something onto the plan view, I can always export that immediately in a number of different file formats: JPEG, GIF, bitmap, what have you. So in this case, we've got contours with labels on them. We've showed how we can change the color ramp. That's the main two ways that you might choose to look at the scalar data that's available as part of a 2D model. I'm going to change this back to my preference, which is filled, and zoom back out a little bit. And one nice thing about these thematically mapped views, at any time I can right-click on this active layer in the Layer Control panel and export the time series data to a CSV or thematic map to a shapefile. So I just right-click on water depth, and I can immediately export the current time step as a CSV, or I can export it to a shapefile. Also, one of the abilities that I have in XP Swim is one of the tools is called XP2D Utility Interface. If I choose to, I can export this entire range of data to a shapefile. So if I wanted to be able to report on depth, I would simply go to the 2D output data, load up the XMDF file for this model, click OK, and it's going to export the elevations or the depth at these grid cells over the course of the solution to a shapefile. Simply hit execute there, and it's going to prompt me when it's finished. Great, it's all finished. And that data is now available if I want to have the depth available as basically a background layer. I can now go to the GIS layer and read in that shapefile that I just created. It's this shapefile right here. And at that point, if I wanted to look at depth at any point in the simulation while I look at another scalar value, it's in the background. And all I have to do is hover my mouse over that grid cell and it shows me the depth. That's a way to store some of this data as background data. You just bring it in as a GIS file. Some of the other data that's useful in interrogating 2D models, or one of the most useful forms of data, is the vector data that we can display. The velocity data, we can show that as vectors. So let's turn on vectors. And again, that's time-sensitive information, so it's going to show me the vectors at any given time step. Let's slide forward in the solution there. And that's a really cluttered, ugly display right there. Doesn't tell me a lot of useful information. Well, vector data typically is more useful when I'm at somewhat of a zoomed-in view. And we can see that the reason that the display is so busy is I have result labels turned on and I have them colored red, right? So let's turn those off. Still cluttered. It's not really getting a whole lot of useful information out of this. Let's zoom in a little bit. So typically in a 2D urban flood model, vector data is important to kind of understand the direction of flow. And in XP Swim, we allow you to thematically map the vectors as well. So I have complete control of whether I want the arrowhead to be fixed or scaled, whether I want the length of the vector to be fixed or scaled, and how I want it scaled, and the same with the shaft width as well. Here I've got it all one size, but just as an example, if we went to length and selected a scaled size and clicked on OK, we'd immediately see a change in how the vectors are displayed. If I zoom in an area of high interest, let's say there's an area of recirculation over here, and I'm going to change the display back to uniform vectors just for the purpose of this part of the demo. Now's when I might want to turn on vector labeling to actually look at the velocity at each one of these areas. If I have an area of recirculating flow, are these high velocity areas of recirculation where that could pose big problems, right? And it's going to give me the value, the velocity value at each one of those points. Another neat thing that we can do with vectors, sorry, that's our value. It wasn't 2,000 meters per second. It's more like 0.243 meters a second. Another neat thing that we can do, though, with some of the data that we have is we can thematically color the vectors and all that kind of thing. I don't find too much value in that typically, but it's there if you need it for a particular type of presentation or a point. If the screen gets too busy, we can always skip a set of results. So if I skip 2 results for the vector data, it's going to more sparsely map the vectors, as you can see, and I can keep changing that until I get a level of discretization that I can use for whatever purpose as part of my output. Another thing that's useful in interrogating the model is to be able to interrogate the grid itself. In XP Swim, if we zoom out to the full extent of the model and I turn on the grid, we get a pretty busy display. If I click on the properties layer, we can see that in this particular model, I have 102,955 cells. So I'm not going to get much value in displaying data associated with each cell at a zoomed out view. But one of the neat features that we have is that we can show the 2D cell center elevation. Click that on, and that only turns on when I get to a certain level of zoom within the model. We also can alter the grid cell display interval. So if I actually wanted to make this a little bit less cluttered, I can have it only show every 4 cells. And I can still thematically render things and look at things, but I don't have such a cluttered screen if I want to show the grid as part of the display. Let's turn that back off. Take it back down to a display interval of 1. And what we'll see when we zoom in to the grid, let's say we're looking at an area of recirculation between different buildings, is we'll now see the cell center elevation at each one of the grid cells, and that can be useful information in interrogating the results. It can also be useful information in some of the reporting that we do, just to have that as a reference in the display. I'm going to turn the grid off and turn depth back on. Zoom out just a little bit. One of the other things that we can do using the XP2D tool that I used to export that depth as a value to be read in as a background layer, that tool also allows us to create what's called a difference file. Let me back up just a second. In this scenario, I actually have a parent and child scenario. I have one called the base and one called the 10-year scenario. And basically all the 10-year scenario is an increased flow rate at the head of the 1D channel. But one of the things that I can do with any two different models is I can look at the differences in any of the scalar values between the two models over the course of a solution. Now, this can be very valuable in evaluating the impact on depth, say, at two different weather events, or the impact on the velocity, the impact on water elevation. What is the difference in those scalar values between two different simulations? And the tool that we give you to do that, and it's a very, I haven't seen this in any other modeling tool, is a 2D results difference generator. Within the XP2D utility interface, I can specify my input files as the XMDF file from the first simulation, and then my 10-year event, as I've described it here. I can specify the name of the output file that I want, and then I hit generate. I won't go through the exercise because it takes a little bit of time to generate this file, but it's a really neat capability. Once the difference file is generated, it's available as a separate results layer, and now I can read it in to my 2D results, and then I'm just interrogating the difference between two different 2D models. That's a pretty advanced capability and can be very useful in comparing two different events. Earlier in the model, we talked about the microphones that we put into, I call them microphones or interrogation points, but we talked about the flow boundary and the head boundaries that we put into the model. These are also, I think, useful ways to interrogate the data, especially when we're looking at flood situations. So the flow boundary was this polyline that we draped across this area of the model. So it's going to capture any flow kind of moving from left to right in this instance along this boundary. So if I highlight that and I go over here to the layer control panel and I right-click on, I right-click on the element itself, excuse me, and I just select graph. It's actually going to give me the graphs for all of the flow boundaries. In this model, I only have two, one called MH overflow, which is up here at the top of the model. The second is called stream overflow, and that's the one that I've highlighted right here. When I click on graph, it's actually giving me both graphs, but we can see in this case, stream overflow, which is the dotted line, is pretty severe. I'm up to about, at one point, at 1 a.m. in the model, I'm up to over 60 cubic meters a second of flow being captured by this flow boundary right here. Well, the flow at my second point, which is called MH overflow, the one up at the top of the model, is barely even graphs. So I'm going to not plot both of them. I'm just going to plot manhole overflow. We can see that for a very brief time, flow comes out of this manhole node up to a point of 0.35 cubic meters a second. Anytime we're looking at a graph like this in XP Solutions, again, it's a neat feature that we have. I think it's worth mentioning that we can go to the customization dialog or the export dialog. We can export these as pretty pictures, but we can also export the time series data into a data file. It's very useful, and sometimes to just have that data at hand to cut and paste into a spreadsheet or what have you. So that's the flow boundary, and let's look at the head boundary. I have a little interrogation point here called intersection. Let me zoom in a little so I can get to it. There we go. And again, I've got several interrogation points in the model. At the intersection here, let's just limit the display to the intersection. We can see the head at the node, and this is reporting information from the grid cell that underlies this interrogation point, from the numeric cell. If I turn on the numeric mesh, we can kind of see which cell that it overlays. This is what's happening at that grid cell. We might also want to show, though, the velocity of flow at that point. We also might want to show the velocity angle at that point. I find these are useful just because instead of creating, looking at an entire layer of information, I can basically identify problem spots within the model, and I can seed the model with as many of these interrogation points as we want. And again, I can import and export that data, which I find very useful. One of the things that we can set up in the 2D job controls as well is called time to inundation. And I find this very useful. This and the ability to map, we call it mapping risk, but it's basically the ability to turn on velocity times depth as an output in the model. That and the ability to show time to inundation are two of the most useful features for the stakeholders that we work with, the emergency planners, emergency responders, what have you. In the 2D job controls, down here in model output, we get to specify the type of time to inundation maps that we want in the model. And these are generated as layers in the layer control panel. And at any time, I can go look at time to the time of inundation. I'm going to expand the layer control so you can read this with me. The duration of inundation is useful information to have, and the time to inundate is useful information to have. So for duration of inundation, longer than 20 minutes, I can now look at it as a thematically rendered filled contour. And again, it can immediately export this as a shapefile for use in reports or what have you. Time to inundation is also very useful for planners. And again, I can thematically map this like I want, but I'm basically going to look at the time to inundate up to 30 minutes at this point. I can also look at time to peak. That can be useful information. But these are scalars that are scalar values that are generated as part of the model process, and they're optional as to whether you want to solve for them or not, but I find them very useful in interrogating 2D models. One of the other things I think that is extremely useful is the ability to map what we define as hazard. And in this case, one of the outputs that I selected was to output hazard as velocity times depth. There are several other formulas in our model for quantifying risk or for calculating risk, I'll put it that way. There's some British methods that are called for in by some of their regulatory bodies. In the U.S., it's kind of up to us as how we want to define it, but I find this one to be very useful. This is a basic down and dirty way to quantify risk. So in my model, I've taken velocity times depth, and I've given it really only 3 color values that it can report as part of the scalar data. Anything up to, and if I hover my mouse over it, anything up to about 0.12, a value of 0.12 V over D, I'm going to show as green because it's really so shallow or it's so slow moving that it doesn't pose a lot of risk. Anything between, let's see what the value is, 0.12 and 0.20, I've classified as yellow. So some risk, but not high risk. But anything above that means I've got some fairly fast-moving water and it's getting kind of deep, or it's fast-moving and shallow. If it's fast enough, can be also very dangerous. I've quantified that as red. But this is a really useful way, in my opinion, to look at quantifying risk when we're looking and interrogating 2D models. So we've looked at time to inundation, and we've looked at risk mapping or hazard mapping. One of the last things I want to show you is the way that we can use time series data, interrogate the model so that we can use the time series data to manage what we call evacuation routes. But it's really kind of a time to risk kind of analysis, for lack of a better way of putting it. In the 2D elements of the model, I can specify that one of the layers I want to create is called evacuation routes. It's part of the 2D model. I'm going to turn off the links. I'm going to turn off the nodes so we have kind of a clean display here. And you can see that I've drawn this polyline right here. So if I go and make that active and edit the data, you can see that along this line, okay, which starts here and ends over here at the left-hand side, I've asked the model to report whenever anything along that line exceeds a value of 0.1. I would consider that a curb height. Maybe I want to color that yellow. I could specify a different range for when automobile traffic should stop traveling in that area. And then I could specify another value when emergency responders should stop traveling in that area. And this is all based on depth, right? The route cutoff is, in this case, based on depth. And the model, when the model runs, it actually displays graphically along this line, and I'm going to turn on the background layer so you can see the yellow a little bit better. So let's turn on this background image, and I might even make it a little bit less transparent. And we'll zoom in, and you can see that along that polyline that I drew, that the time to inundation for the yellow level was 0.28 hours. The time to inundation for the higher level of risk was 1 hour at this point in the map. And we did not achieve the third point, which was 0.8 meters, anywhere along the evacuation route. But this is basically going to give you a time to inundation along a polyline. And that's a great thing for emergency planners to have. And so it's information that's easy to get out of the model and into their hands just by drawing different polylines throughout the model. And that's kind of, in summary, what I was going to show to you guys today.
Great. Thank you very much, John, for all the information that you've given us today. Hopefully it's going to help some folks in their modeling coming up. And thank you, everybody, for joining us today. Happy modeling, and enjoy the rest of your day.
Thanks, everybody.